How microbes survive deep underground without sunlight. Secrets of subterranean life. Imagine a world without sunlight, deep within the Earth's core. It's a place where life as we know it shouldn't exist. But here's the mind-boggling truth. Microorganisms thrive in these extreme conditions, and it's all thanks to some incredible chemical reactions triggered by tectonic faults. Scientists from China have unraveled this fascinating mystery, and their findings are nothing short of groundbreaking. Published in Science Advances, their study reveals that life underground isn't as limited as we once thought. The mechanism of survival. Professors He Hongping and Zhu Jiangxi from the Guangzhou Institute of Geochemistry have delved into the processes happening in tectonic fault zones. These zones, where the Earth's crust moves and creates fractures in rocks, are like hidden laboratories. The researchers discovered that the formation of these cracks releases free radicals, which are highly reactive particles. These particles split water molecules, producing hydrogen and hydrogen peroxide. But here's where it gets interesting. This process creates a redox gradient, which initiates chemical reactions involving iron. Iron can switch between its ferrous and ferric states, and this supports biochemical cycles of carbon, nitrogen, and sulfur. These cycles provide microorganisms with the essential substances they need to survive and thrive, even in the absence of sunlight and organic compounds. The power of tectonic faults. One of the most significant findings is the role of tectonic faults in producing vast amounts of hydrogen. During earthquakes, these faults can generate up to 100,000 times more hydrogen than other known mechanisms, like serpentinization or radiolysis. This makes fault zones a critical energy source for the subsurface biosphere, allowing microorganisms to flourish kilometers beneath the surface, in conditions that would be deadly to most life forms. Scientific significance and astrobiology. This research revolutionizes our understanding of Earth's subsurface biosphere. It challenges the traditional belief that life deep underground relies solely on limited energy sources. Now, we know that tectonic faults create a stable and powerful energy source, capable of sustaining complex microbial ecosystems. And this is the part most people miss. These findings have huge implications for astrobiology. The conditions created by tectonic activity on Earth could be similar to those on other rocky planets, like Mars or the moons of Jupiter and Saturn. The hydrogen and redox reactions identified in this study could be our key to unlocking the secrets of life in subsurface oceans or rock formations on other celestial bodies. Future explorations and interdisciplinary research. The authors of this study emphasize that their work opens up exciting new avenues for exploring underground life. Future studies will focus on understanding how different types of tectonic faults impact microbial communities, and identifying the most resilient microorganisms in these environments. Researchers also plan to simulate similar processes on other planets, offering a deeper understanding of the potential for extraterrestrial life. This discovery highlights the power of interdisciplinary research, bringing together geochemistry, microbiology, and planetary science. By understanding how life survives in Earth's extreme environments, we might just unlock the mysteries of biospheres beyond our planet. In conclusion, the work of these Chinese scientists has changed our perception of life on Earth. Tectonic faults, with their ability to generate hydrogen and hydrogen peroxide, provide the energy needed for microorganisms to survive without sunlight. This not only expands our knowledge of the subsurface biosphere, but also offers a new lens through which to search for life in the universe. It inspires us to continue exploring both on Earth and in the vastness of space, as we uncover the resilience and diversity of life. Life under Earth. How cracked rocks power deep biosphere and potential life on other planets. What if I told you that earthquakes might be the secret fuel powering an invisible underground universe of life? Forget photosynthesis. Groundbreaking research reveals how Earth's deepest ecosystems survive on energy unleashed by cracking rocks, rewriting our understanding of what sustains life. And this discovery could reshape how we hunt for aliens. A team from the Guangzhou Institute of Geochemistry, Chinese Academy of Sciences, has cracked the code of how microbes thrive miles below Earth's surface, far beyond sunlight's reach. Professors He Hongping and Zhu Jiangxi recreated earthquake-like conditions in their lab, revealing a startling truth. When rocks fracture under pressure, they release explosive bursts of hydrogen gas and hydrogen peroxide, essentially creating underground energy bars for microbial life. But here's where it gets controversial. This process produces up to 100,000 times more hydrogen than other known geological reactions. First author Zhao Wu compares it to flipping millions of microscopic switches simultaneously during seismic activity. While sunlight vanishes within meters of bedrock, Earth's deep biosphere, home to 15% of all planetary biomass, runs on this violent chemistry. Let's break it down for beginners. When earthquakes or even tiny tremors crack quartz or basalt rocks, they create free radicals, highly reactive particles. These radicals act like molecular scissors, splitting water into hydrogen, a fuel, and hydrogen peroxide, an oxidizer. Imagine a microbe's dream buffet, all served up by tectonic tantrums. The numbers are staggering. Lab experiments show fault movements generating 160 micromoles of hydrogen in 4 hours. Over a year, this could produce 33.1 moles per square yard, enough to sustain dense microbial cities. To put this in perspective, many underground microbes survive on just 0.00000000100 watts, and whether it is energy each. A single moderate earthquake could power them for millennia. Here's the twist most miss. Hydrogen alone isn't enough. Life needs a yin-yang energy exchange. The study found that fractured rocks also trigger an ion redox cycle. Think of it as nature's battery. Hydrogen converts rust-like ferric iron, Fe cubed, into ferrous iron, Fe cubed, while hydrogen peroxide reverses the process. Microbes exploit this endless dance, using iron as their metabolic middleman. Field evidence backs this up. Scientists detected hydrogen spikes in Tibetan hot springs hours before quakes. In Canadian bedrock, iron shifts between forms over years, proving microbes stay active between quakes by snacking on these chemical radiants. Even glaciers grinding rocks release hydrogen, proving this isn't just an earthquake story, it's a planetary survival strategy. Now, the cosmic kicker. If rock fractures can power life on Earth, why not on Mars or icy moons like Europa? Mars' cracked crust and shifting iron minerals could host similar chemistry. Rovers might soon hunt for hydrogen leaks or rust patterns as biosignatures. As study co-author Zhu notes, life could be running its circuits anywhere electrons find a path. But let's get real. Is this energy enough? Critics argue that earthquakes are too rare to sustain ecosystems. Yet the data shows even 0.000 microsecond of mechanical energy converted to chemical power from rock fractures creates temporary oases. Microbes then enter ultra-low power hibernation, surviving on whispers of energy for millennia, as seen in South Africa's gold mines. Here's the burning question. If life can thrive on geological chaos, does every rocky planet with tectonic activity automatically get a ticket to the life game? Could dead-looking worlds like Mars secretly host quake-fed microbes? The study, published in Science Advances, forces us to rethink habitability. Forget water alone. We need to hunt for planetary stress fractures. As missions like NASA's Mars sample return loom, this research gives scientists new targets. Follow the cracks, follow the rust, follow the hydrogen. What's your take? Could earthquakes be universal life support systems, or could Earth's deep biosphere a fluke? Drop your thoughts below. Let's get tectonic in the comments. Hungry for more mind-bending science? Subscribe to our newsletter for weekly deep dives. And don't miss EarthSnap, the free app that lets you explore our planet's wonders, including earthquake things, through your phone. Intraterrestrials. Discovering alien life beneath our feet. Life as we know it is just the tip of the iceberg. What if it's not? While we gaze up at the stars, hoping to find life beyond Earth, a frontier far wilder exists right beneath our feet. A hidden biosphere of bizarre microbes thriving in the planet's crust. In her groundbreaking book, Intraterrestrials, Discovering the Strangest Life on Earth, scientist Karen G. Lloyd frankly challenges our narrow definition of habitable environments by revealing a realm where sunlight and oxygen are irrelevant. But here's where it gets controversial. For decades, we thought Earth's deep subsurface was an inhospitable wasteland. Lloyd's work shatters that illusion, documenting microbial life flourishing in Antarctic ice caves, volcanic hydrothermal vents, and the crushing pressure of deep ocean crust. These creatures don't need photosynthesis. They eat rocks. The root of the confusion. There's no such thing as a sterile subsurface, Lloyd argues. Yet even well-funded research projects struggle to conceptualize these chemical-driven organisms. She attributes this to our sun-centric biases, but her discoveries reveal a life-form alliance with minerals rather than plants. 2 survival strategies. Lloyd identifies 2 distinct microbial groups. One chemosynthesizers that convert geochemical reactants, like those between water and hot rocks, into energy and biomass. 2 heterotrophs that scavenge organic leftovers from circus life, acting as deep underground recyclers. But this raises a mind-blowing question. What happens when we dig deeper? Japan's Chiku ship, the ocean drilling equivalent of a Mars rover, has pierced 1.2 kilometers into seafloor crust. Yet the mantle, a 2,900-kilometer wide rock strength beneath it, remains untouched. Could microscopic life writhe within that uncharted expanse? The undead microbes that confuse biologists. Meet Desilvarudes audacthiator, the radiation-guzzling bacterium, found 2.8 kilometers deep in South African gold mines. It survives where sunlight can't reach, feeding on uranium for radioactive decay, a process that might sustain it for millennia. Other microbes seem to enter dormancy, existing in a grayscale zone between life and death for thousands of years. Lloyd poses a provocative question. Are these organisms evolved to wait out geological eras, or are they simply durable? The astrobiological paradox. If intraterrestrials thrive deep within Earth, why couldn't parallel ecosystems exist on Mars, Venus, or moons like Europa? Yet Lloyd warns this raises troubling questions for our exoplanet hunts. These life forms don't alter atmospheric gases. They leave no detectable biosignatures. They might become undetectable even to our most advanced telescopic sensors. But here's the kicker. This realization challenges core astrobiology assumptions. If subsurface life is common, our current methods might fail to spot it even when it exists. As Lloyd asserts, this isn't speculation. It's evidence-based observation from Earth's own depths. This shifts the conversation dramatically. When searching for alien life, should we prioritize the surfaces of exoplanets or their uncharted underbelly? Lloyd doesn't provide easy answers, but challenges readers to adjust their expectations. Assuming life requires sunlight limits how we explore the universe. The final sprint for answers. As drilling technology improves, Lloyd's work becomes more critical. Mantle life, if it exists, would redefine our understanding of planetary habitability. It might also embarrass our current astrobiological strategies, as any planet with liquid water and rocks becomes a potential candidate for life, regardless of surface conditions. But what if we're looking for life in all the wrong places?